Okay, back everybody to Python for Physics. We're on week 6, first day of the week 6, and today we're pretty excited about this lecture. We're gonna do something new, something that we haven't done before. As I mentioned towards the beginning of this class, this is a class that Ted and I have taught before. We taught this last year, and it's a class that is targeted to mainly high school students, but also it turns out that it's useful for anybody interested in learning a little bit about programming and how to use it for doing research, in particular with physics. But as you've already seen, some of the problems that we've considered are general, right? Regarding data analysis, for example, doing fits, those are universally useful tools. Because we wanted to target this class to students that were in high school, we didn't want to assume that you had any calculus background. And so the shortcoming of this, right, is that a lot of physics involves calculus. And so this limits us quite a bit on what we can cover. But then what Ted and I realized is that, why can't we just introduce a little bit of calculus concepts to you? And so that's what this is going to be. This is what we're going to cover today. We're going to introduce ideas of rate of change, calculus, and differential equations. And we're going to show you how to solve some simple differential equations. But what we're going to do is not assume that you've taken a calculus class at all. And so, in fact, we're not going to assume that you know anything but algebra. And a little bit of programming. And so if you haven't seen calculus class, I hope this is a nice introduction into calculus. If you have seen calculus and you've taken a calculus class, we're still going to introduce concepts that perhaps you haven't used before, which involve solving differential equations numerically. And this is going to let us do some more interesting concepts later on next week. And so that's what this week is going to be about. And I'll start with the same administrative introduction that we start every single class, which is, if you're new to the class, welcome. And what you should do is send us an email right here. Send us an email to this email address, python4physics@odu.edu. And what this does is that you will get an automatic reply with all these various different links, which tells you about all the materials that we've covered so far and all the materials associated with this class, so we can try to catch you up. The first thing you will see is the website of our class, so you can see that over here. The second thing is a chat where you can have, it's a Slack chat where you can have discussions with us, as well as the TAs and all the other students in the class. You do have to be 16 years of age or older to use Slack. If you're in the live stream, you've already used this link, but perhaps this might be useful as well. Also, you can see all of the recordings of the REYES activities on this page. There's going to be various different archive tabs, including the Python for Physics one, which you can find directly here. But I would encourage you to go to the REYES page and see all the material that we generated for you. And lastly, we have a Dropbox folder where we share all of the content, including our code, and we're going to keep that available for you indefinitely. And so you can find all the material here on this Dropbox link. This is what our page looks like. We haven't updated it in a little while, but we've tried to answer some of the main general questions needed to get you involved in the class. So you can go check that out if you're new to the class. And finally, we've also have a Dropbox folder for all the material that, there's a Dropbox folder for you, the students, to share your code with us. And so if you want to have access to this Dropbox folder, what you have to do is send us an email with this on the subject line. This is just send the same email to here with the subject line. This Dropbox folder is different than the other one. So this is one where you will have editing rights. And so you'll be able to put your material there and be able to edit the folders as you wish. So what I'll do is start with a little bit of review of what we've seen so far and try to answer your questions regarding any of the previous topics that we've covered. But before I do that, why don't you go ahead and tell us how you're doing? How are things on your side of the world? Are you enjoying the class? Is there anything that you want us to cover that we haven't covered? Those kinds of things are exactly what we wish to hear from you. So that being said, I'll wait for your replies and your comments and to hear how you're doing. And Before we read those, let me start with a little bit of review of what we covered in last week's classes. So first, basically we introduced several concepts regarding modeling of spin particles, and in particular we introduced a simple model called the Ising model. And the Ising model is a model that was introduced, was first studied by Ernst Ising, and what we did is we introduced a one-dimensional analog of this problem. And in this system, we put particles, we put spins in a little chain, we wrap that chain in a loop, so it's a periodic system, so it's a line that is periodic. We put the particles either to have spin up or spin down, and this is the kind of cartoons that we played with quite a bit. And so a particular configuration of these spins was associated with a given state of the system. And here you can see, so I have a system, I have a state, I have particle 1 with a spin up, particle 2 with a spin down, particle 3 with a spin down, particle 4 with a spin up, particle 5 with a spin up, and particle 6 with a spin down. We gave numerical values to these different configurations of up versus down. So up meant that the value of the spin was 1. When the spin was pointing down, we gave it a value of -1. And after that, having this mathematical representations of the spins, this allowed us to then write the energy of the system as a function of the spins of the system. And so we wrote the energy in terms of 3 different terms, one that is multiplied by this factor A, another one that is multiplied by the factor B, and another one that is multiplied by the factor C. A, B, and C are just numerical constants that depend on the property of the system that we're interested in. So the first term, it was associated with nearest neighbors interactions. So you have a spin in position I, and is interacting with a neighbor that is just a position I plus 1. This was associated with next to nearest neighbors interactions. So you had here a spin at position I, and then the next one at I plus 2. So 2 steps to the side. And this other term was just associated with the background field. So the background field can couple and interact with the total spin of the system. And so here you just have a multiplication, a term multiplying the whole spin of the system. And so here we had little tables explaining what this products of Si times Si plus 1 and as well as Si times Si plus 2 for different spin for this example where we're running I 1 through 6. And so I would encourage you to look at this closely so you have a good understanding of what each one of these terms is doing. And so we had several exercises. I think some of you started on this, and I think some of you are still catching up. And so I will walk through the exercises, and perhaps you can ask us what are the issues that you're struggling with. And I think this is, as I mentioned, this is a good exercise because it teaches many different skills, not just related to physics, but also just maneuvering functions that depend on arrays that can be of arbitrary size, making lists of many different arrays, looping over all these, sorting through a given variable, and so forth. And so if these things don't quite make sense to you, what I would encourage you is to go back to the previous lectures and go through them a little bit carefully. But the first exercise was just to write code that calculates the energy of a system of spins as a function of A and B and C for a state that has arbitrary length, okay? And so I give you an example of my code. I use this function rotate that rotates over all the possible spins. And I walked through this somewhat I think we actually walked through this twice and with quite a bit of care. So hopefully that makes sense. And so this was the first bit that I wanted you to reproduce. The second part is to write code for all the possible spin configurations. And so if you have a spin system, if you have a system of n spins, then you can have 2 to the n possible states. And I I wrote this down, and I also explain why this is the case in quite a bit of detail. And so here's code that I wrote doing that. But what I always encourage you to do is you to sit down, and this is something that Ted emphasized, to write down your own code and the logic of your code, your pseudocode in pen and paper, and then try to implement this afterwards while you're making little comments of each logical point of your code, okay? And so I would encourage you to do this independently of my code, but if you get stuck, try to perhaps understand my code. Exercise 3 to 6 was just to get the ground state and degeneracy of all these different examples. Remember, degeneracy was this concept that we introduced for describing states that have the same energy, even though the states may look different. And this was associated with asymmetry present in the system. And we talked about that in quite a bit of detail. The last exercise was to, and I can't remember, sorry, there's a typo. This is 3 to 7, right? Not 3 to 6. So let's fix that. Typo fix. And exercise 8, I gave you a system of 10 spins. Okay, so we had this number of distinct states, quite a bit, okay? And we fix A and B to be these values, and then we asked to vary C continuously from 0 to -3, okay? And we argued as to what is at some value of C, so at C equals 0, these have to be the ground states, okay? These two are degenerate, and they both correspond to the lowest energy. And then as you take C to negative infinity, then this becomes the ground state, okay? And so I suggest this suggestive exercise is saying that this transition from this being the ground state to this being the ground state happens in this region of values of C. So you don't have to take C to infinity, in fact. And so the question is, what values of C is this no longer the ground state? And at what values of C is this now the ground state, okay? And so one way to visualize this is to just plot the energy as a function of C. And here what I've done is that I made 3 different plots, and I overlaid them on top of each other. The first one is a red, which is not absolutely clear. So let me shift it a little bit. You can see how the magic happens. Okay, so the first one is the energy of these states as a function of C, right? And the thing here is that this system has a total spin of 0, right? I add up 1 minus 1, 0, 1 minus 1, 0, and so forth and so forth. So the total spin is 0, right? And so if you look back at the energy of the system, right, you have a term that multiplies this, or a constant that multiplies this, another constant that multiplies this. Here, this is the total spin of the system, right? And so what does that tell me? If the total spin of the system is 0, then the term that is multiplying C is equal to 0, which means that this energy for a system that the total spin is 0 has to be independent of the value that I choose for C. Okay, so it should be the same for any value of C. Well, let's go back. You see? Aha, this energy, the red one, is flat as a function of C. That's what it means to be independent of C. You pick C to be 1, -1, and I get this value. I pick it to be -2, I get the same value. And for any value, I'll get the same value. So it's independent of C. Good. This other line, the green line, is the energy of the system, which does have spin, right? And so it does depend on the value of C. Good. And it's linear as a function of C. Good. That has to be the case, right? Because the energy depends linearly on C. And what I'm plotting in black is the actual ground state for any value of C. And you can see that above this circle, it agrees with the red line. Below this circle, it agrees with this green line. And that's what we expected. You see there's one point where it transitions to another spin configuration. Let's zoom in. So you see the state goes from being this to now being this, which I didn't label what it is, but you can see there's a kink saying there's a transition to a new ground state. And now there's another kink to a transition to another ground state. and then finally, a final kink. And we know this is the last one because we argued why it had to be, as you take C to infinity or negative infinity, this had to be the ground state. And we've seen that it transitions to this being the ground state. Okay, so this is exactly what I was hoping that you would try to reproduce and find the values of this C over here and this other value of C over here. Okay, so hopefully you've been able to make some progress in that, and you can send us questions if you're stuck on anything. And what I'll do is tell you what we're going to do next. Okay, but first, let me give time for our TAs to tell me if there's any questions or comments that we should read aloud. So I'll pass it on to the TAs for a second.
We did get a nice message from Brian Benitez from Mexicali, Mexico, in response to you asking how everyone was doing. Brian says, nice to hear you guys every morning. Very interesting topics and very useful. Always wanted to learn Python, and learn from a physics view makes it better.
That's great. Thanks, Brian.
And for now, I think that's it.
Okay, cool. Then why don't we get started? We have a lot to cover today. So the natural question is, what's next? What are we going to cover? Obviously, we can cover an infinite amount of stuff regarding computing and physics, but we only have a finite amount of time, so we picked topics that we thought would be interesting. And these are ones that we already mentioned. So first, what we are going to introduce this week is concepts behind calculus. And in fact, I'll try to motivate it first with physics, obviously, right? We're physicists, so I'm going to try to give you the simplest example in where calculus may be relevant in physics. And then we're going to start towards perhaps the end of today or the beginning of Thursday, we're going to start introducing differential equations. And so we're going to walk you through how to solve these bit by bit, okay? So we're going to take this slow, assuming that most of you have not seen this before. So that's the goal for this week. Next, after this week, on Tuesday, we're going to have Dr. Fatma Aslam, who's part of the Python for Physics crew. She's going to give us a nice introduction into quantum mechanics next Tuesday. So you should look forward to that. And this is going to be independent to everything else that you've been learning, okay? So this is going to be just a fun side note, okay? And then what we figured is that since we're going to be teaching differential equations, there's many differential equations we can consider in physics, and they can be arbitrarily complex and interesting. But what we thought about is that although we're physicists, we are all living in the middle of a pandemic. And I'm sure you have seen many graphs of trying to model the behavior of the pandemic as a function of time. And so what we thought is that what we can do is look at closely from a physicist standpoint, look at closely at these simple models for infectious diseases, and look at their event. They all amount to solving some set of differential equations. And in fact, the tools that we're going to be learning about for solving differential equations are going to be useful for solving these models as a function, so the number of cases as a function of time. And so what we're going to do is give you a little introduction into these models and then try to solve them ourselves, okay? So we figured that would be very timely, and I think hopefully it will give you a little bit of better guidance in understanding what is the data what is the data and the expectation of behaviors of the cases that we're seeing around the world, okay? So that's our outlook. That's what we're going to be doing for the next couple of weeks. So hopefully you find that interesting and choose to continue joining us. Okay, so let's start introducing basic concepts of calculus in the context of physics. And so what I'm going to be using, I'm going to be thinking about the change of different functions with respect to other variables, okay? So we're going to be interested in change. And so we're going to be evaluating the change of different quantities. And so we're going to be using some notation that perhaps is not common to everybody. And so we figured we can just introduce it here right away. So if we consider some function which depends on some independent variable, x, we're going to label that function f of x. Okay, so we're going to be playing with different symbols, but you're going to see me using f of x quite a bit. And if at some point x takes on the value of x1, and at some later time it takes a different value of x2, then we can define the change in x from x1 to x2 using the Greek letter delta. Okay, so delta of x is going to refer to this symbol. Delta x is going to refer to the change in x. So it's going to be the final point in x minus the initial point. Okay? So similarly, we can define the change in f in this interval, right? Where we're taking x from x1 to x2. So in that interval, the change in f, this function, is just going to be the value of f at x2 minus the original value of f evaluated at x equals 1, or at x1, okay? And so all this is trying to do is that introduce the symbol delta. So whenever I put delta in front of a function, which could be that function could be the independent variable, and this time x, I just mean the difference of that over some period. Same thing for delta f. It's just going to be the change of that function, right? And I can be thinking about time. And so I could define delta t as a change in time. And so delta is just the change, okay? So that's just all that means. And at times, it's going to be, so later on, when we're solving, when we're evaluating derivatives, which is what we're going to be going towards, which is the first object that you see in calculus, what we're going to be interested in is evaluating differences of f of some function in a particular way. And in particular, we're going to be using where the separation between the initial and the final point is dictated by some parameter a. Okay, so in particular, we're going to be defining the initial point in x1 to be x minus a, and the final point in x to be x2, which is going to be x plus a. And you see the shift, we've defined the shift, the difference between x1 and x2 to be separated by a length of 2a, right? So the difference between the two of them is a length 2a. And so that defines what a is, okay? A could be anything really, but it's defined by the difference between the final point and the initial point, okay? And so sometimes we're going to be introducing this explicit value of a in our delta. And so sometimes you will see this notation where you have delta a, f, x. And what that means is evaluate f at x plus a, and then subtract it at x minus a, okay? So that's all it's going to mean. It's going to be very explicit, and we're going to cover this back again, okay? But if you haven't seen this notations, it's always important to see things over and over again, and then eventually it starts to sink in. It becomes second nature, and eventually you actually understand it. So it's important to see it more than once. So this is a notation that we're using, okay? Having introduced the notation, and I'll make it explicitly over and over again, let me now start describing the basics of where we might be interested in evaluating change of objects in physics. And the simplest place where this appears is once we start trying to describe the motion of objects. So if you have any object, you can start asking questions about the behavior of that object. And we then have to start identifying different mathematical or different quantities that describe the answers or can give us a quantitative answer to these different questions. So here what I'm doing is that I have some question that we would ask about some object that is moving. In this case, we have a skater that is moving down a hill. And so we can try to ask questions about this object, and then the answers are going to be in the form of these quantities, okay? So the first question is, where is the object? And the answer would be a position, right? So you tell me where, I ask you, where's the object? And you would tell me somewhere along the x-axis and somewhere along the y-axis, or so forth, okay? So it's going to be in some plane or some three-dimensional surface, and you're going to give me the coordinate associated with that position. And so the position is a descriptive quantity. Then I can ask, how far has it traveled? You know, assuming that it started at some point and that it's traveled to some other location at some later time. And the quantities that would describe this are either the displacement or the distance. Both of these are important. But of course, we can start asking questions about where is it going and how far is it going, right? And so this is now telling me associated not just with the distance that is traveled or the displacement of it, but how much time it took to get there. And the quantities that tell us about this are speed and velocity, quite naturally. And these are going to be associated with rates of change of these objects as a function of time. And then the last one is, you know, is it speeding up? Is it slowing down? Or is it just staying at the same rate? And this is acceleration. So acceleration is the quantity that tells us about whether the object is moving at faster or if it's going to be the velocity is increasing or decreasing, okay? And so perhaps these are concepts that are quite natural to you and perhaps you've seen them, but it doesn't hurt to just get a little refresher on what these mean. And so here are some simple introductions into each one of these. And so first, let's think about position, okay? Where is the object located, right? And so to locate an object, first we have to define some coordinate system. We have to define the object relative to some frame that is fixed. Either it's fixed or it's moving at some constant velocity. Here we're going to assume that it's just fixed. And so this is going to be our reference frame, and we're going to have to define some reference point inside of that frame, which is often the origin, which is the point where the position is 0, okay? And so this is my coordinate system in this case. So if I think about one-dimensional coordinate system, I just have to define the x-axis. So this is labeling the position. Here I've labeled in units of meters, because those are the SI units for position. And then objects that are towards the right, they're going to be at positive values of position, while objects that are towards the left of the origin are going to be at negative values of position, right? And so if I move an object to a position right here, what this will tell us is that the position of the ball is at 2 meters, okay? So it's at 1, 2 tick marks to the right, and the value is positive, telling us that it's towards the right of the origin. But of course, I can put this object towards the left, 2 tick marks towards the left, and then the answer as to what its position is, it would then be -2 meters, right? It would be I would go 1 step to the left and another step, and that's -2 meters. And the negative sign is telling us about the direction of the object, right? And so in this case, it's positive, while here is negative, is the position towards the left. And so distance and displacements are two concepts that are they're closely related, but their definitions are very close to each other, but they're very different. So first, distance is the total ground that is covered while you move the object. So if the object travels some distance, so travels around for some amount, then the distance would be the total ground that is covered during the time that the object was traveling. While displacement is a vector. So it points from where you started, so from where the object started to where the object ended up. And so although these sound very close to each other, they're in fact, they can be quite different, okay? So imagine that the object has gone from 0 to 2, then the displacement is a vector that points from 0 to 2, okay? And so what is defined is delta x is equal to the final position minus the initial position, which is 2 minus 0, so it's equal to 2, and it's positive, right? The displacement in this case, though, again, it would be the final position minus the initial position. In this case, the final position is -2. The initial position is 0, so I'm subtracting 0. And so I'm left with -2. And so you see the displacements are quite different in this case. They're off by a sign, while the distances are exactly the same. The distance is just the length of this vector, okay? So they're closely related. They're not exactly the same. Okay, so here I'm just putting a simple conceptual question to test that you're getting comfortable with these ideas. And so first, let me just read the question. Then I'll give a pause. You're welcome to try to answer, but I might not wait for you. Okay. So first, I have a car that moves 32 kilometers to the right, and then reverses direction and travels 120 kilometers to the left. And so first, what is the displacement of the car? And you have these options: A, 72 kilometers; B, -72 kilometers; C, 122 kilometers, so forth and so forth. Okay. So then the question is, which one of these is true? Okay, good. 2, what is the distance traveled by the car? Okay, so this is different, right? This is asking about the displacement. This is asking about distance. So distance, you have the same options, right? So the question is, what is the total distance covered in this case? Okay. So I'll give you a second. I think the delay is too long. And then I would just answer the question for you. Okay. Okay. So the answers, of course, are -48 and 192. How do we know this? Okay. So first, the first question is asking about the displacement, right? And so the displacement is I first go towards the right, and then I go towards the left, and I go further to the left than to the right. Okay. So I went 72 to the right, but I went 120 towards the left. Okay. So you know that the number had to be negative. So that rules out all the positive numbers. Okay. And then the distance is just going to be, so not the distance, the overall sign, the actual value, you can just get by grabbing the final position, subtracting it by the initial position, or you can just, which you can relate by the change in x1, which is the first interval, plus the change in x2, which is the second interval. And so you can calculate the final minus initial for this case and the final minus initial for this case, and you would get this number. Okay. The second one, it's closely related, but what you're interested in is in the distance. And so you're interested in the distance first. So you're interested in the total ground that is covered. And so you're interested in going and evaluating this distance right here, which is always positive, right? So the distance here would be a positive number, plus the distance covered from here, from this point to this point, which is also a positive number. And so you use that up 72 plus 120, which gives you 192. And so that's that number. Okay, so hopefully that makes sense. And so for the most part, we're going to be interested in displacements, but it's also important to know distances. And so once we start describing not just the position, but we want to start describing objects that are moving, right? Then what we're interested in is in the motion. And we're interested in trying to figure out how much distance is it covering, or how much is it traveling in some interval of time, okay? And so position is where you are and how far you've traveled. Speed is the first object that you can think about that is telling us how fast we are actually moving. And so speed, what we're going to see is that there's two objects that we can define that are going to be related to rates of change. One is speed, the other one is velocity, and they're closely related, but they're not exactly the same, okay? just like position and displacement. Closely related, not exactly the same. And so speed, what we can define is first the average speed. And this is just by definition, the total distance that traveled divided by the total time that it took to travel that distance. Okay, and I think this is quite intuitive. You can think about traveling, some long distance, and you can go from here, let's say from here Norfolk to Richmond, and you calculate the distance that you've traveled and the time that it took you, and you take that distance divided by the time, and it's going to be about the speed that you're going to see in your speedometer in your car, that the number that you saw roughly fluctuating when you're traveling. So that would be close to maybe 60 miles per hour for me or so, okay? And so that would be about the average speed that you're covering. But as I said, speed and velocity are closely related. They're both telling us about motion, but they are not exactly the same. And the difference between them is the fact that direction really matters in describing, in particular, velocity. So velocity itself is a vector, and it has meaning. It has a magnitude, it has a value, and it has a direction, okay? And so that's what it means to be a vector. So you have to tell me a value that it has, or a magnitude that it has, and which way is it pointing, okay? So examples of this, of these are, if you have some speed, let's say, so you're saying some object is moving at 30 miles per hour, then you have to give it direction, eastward, okay? Or 2 meters per second and is up, or 25 kilometers per second towards Richmond, okay? So these would be velocities. And speed can be the magnitude of the velocity, okay? So you can just grab the values. So in this case, the speed could be this value of 30 miles per hour, okay? And so first, what we can define is the average velocity. So the average velocity, it has a very similar definition as the average speed, except in speed, we had the distance, the average distance, the total distance covered, while here, what we have is the displacement, okay? So if you have the average speed is equal to the displacement over the time that it took, okay? And so you're seeing all I have to then do is just use the symbol delta x, right? And so delta x is going to be the change in displacement, and then delta t is a change in time, okay? Or sorry, delta x is the change in x, which is the displacement, divided by the change in time. And so it's just equal to x2 minus x1 divided by t2 minus t1, okay? And the standard units are meters per second, okay? And the little bar on top is what we used before, just tells us that we're calculating an average here. This is not the value of the speed or the velocity at that point, but is the average over some time interval defined by this delta t, okay? Okay, so the first thing you can try to imagine is trying to graph velocity. And so to do this, what we can do is just make a plot in x, okay? So I have x as a function of time, okay? So x is varying as a function of time. Time, in this case, is an independent variable. X is a dependent variable. And so imagine that at some point t1, so t1 where the time is equal to 15 seconds, your position is at x1, which is equal to 60, okay? So x1 is equal to this value. And at t2, which is equal to 30 seconds, your position is 100 meters per second, okay? So you have these 2 points. And so what we have now is plotted the position versus time, okay? So we can assuming that we're moving at a constant rate, we can just connect these dots, and so here's a linear line that connects these 2 points, okay? So let me just move these up a little bit, and then first what we can do is calculate the change in time, which is just the difference. It's just this length right here, okay? And then we can calculate the change in x, which is just denoted by this line going from 60 to 120, okay? And so what you notice, right, is that the slope, in this case, of this line connecting these 2 points is nothing more than the change in the height divided by the change in time, okay? But that's also nothing else than the velocity, okay? And so having these points and information, we can calculate the slope, and that gives us the velocity. And in other words, if I can calculate the slope of a graph, if you give me any graph, the slope is going to give me the velocity, or it's going to give me the average velocity between 2 different points, okay? And so this is quite nice, and this is actually a way for us to start going from having an average definition of velocities to having an instantaneous definition of velocity, right? If we're interested in defining the velocity at that one moment, instant, which in general is useful, versus defining the average velocity between 2 different points, we can use this definition of slopes, okay? And so the instantaneous velocity is a vector, just like velocity itself, which is telling us how fast that particle is moving at that given instant, okay? And so what we can do is, here is a more general graph plot where I'm plotting the position of the object in red as a function of time, okay? And so what we can do is grab the average definition, right? So we can grab this definition, and you see that if I separate the 2 points quite a bit, I have the rise over here, the run over here, and so the slope of this graph will give me the velocity, right? And as I said, this will give me the average over this region, right? But what we can start doing is taking the limit as the separation from the initial point to the final point in time becomes increasingly smaller, okay? And so this definition where I grab delta x divided by delta t, and I take t, that's delta t, sorry, I take delta t to 0, that is the definition of the instantaneous velocity. And that is going to be the slope of this function right at that point, okay? And this is known as the derivative of x with respect to time. You don't have to know what this is just yet. What we're going to use, in fact, is this definition right here, where we're going to grab the function that we're interested in, and we're going to want to evaluate the rate of change of this with respect to its independent variable in the limit that the gap, the difference between the change in the independent variable goes to 0. So we're going to use this definition, okay? But just so you know, this is symbolically represented, this limit is mathematically represented in calculus with this value d, okay? And delta is the Greek letter that is for d, essentially, okay? And so you see d, the Greek d, and here you see our Latin d, okay? And so the instantaneous velocity is the tangent to the curve at that point, okay? So that's what definition of it, but we don't have to worry about that too much. Okay, so this has been all about velocities and speed, and we're going to focus most on velocity. So we can ask the same question about acceleration. So what is acceleration? So acceleration is the change in the velocity, okay? Just like velocity is a change in the position, acceleration is the change in the velocity. And it's just as in the velocity, which is a vector, the velocity itself, the acceleration itself, is also a vector. And so we can define, again, following the same steps, the average acceleration. And what it is telling us is whether the speed, the velocity is changing. And you can imagine as you accelerate a car from 0 and it's not moving, to 20 miles an hour, you've increased the speed, and so you've changed, or you've increased the speed and the velocity, and so it's gone from 0 to some higher number. So that means that you've had to accelerate. The acceleration during that time was non-zero. Okay, so the average acceleration is nothing more than the change in velocity divided by the change in time. So it's the final velocity minus the initial velocity divided by the change in time. Remember, the velocities themselves are change of positions with respect to time. Okay, and so here what you can see already is that the velocity has units of meters per second. This ratio has to have units of meters per second squared. Okay, and so as an example, here's a car. I mean, here's essentially a very similar example to the one that I just said. You have a car that is moving initially at 17 meters per second, or 15 meters per second, sorry, and it slows down to 5 meters per second in 5 seconds. Okay, so it went from some high speed or high velocity to a lower velocity. And so then the question is, what is the average acceleration of the object? And so you can just apply this definition, right? The average acceleration is just equal to the final velocity minus initial velocity divided by the change in time. The final velocity is 5, the initial one is 15, so 5 minus 15, that's equal to negative 10, divided by the change in time, where the final one is 5, the initial time was 0, and so negative 10 divided by 5, that's equal to negative 2. Easy, right? And so that's telling you the average acceleration. You see that it's a negative number, so it's pointing towards the left. The object is moving towards the right, the acceleration is pointing towards the left, and so it's forcing the object to move slower and slower. Okay, and so notice that the velocity is decreasing, the acceleration is negative, and that tells us that the object is decelerating. Okay, that's what the definition of the deceleration is, that this velocity is decreasing. Okay, so here's a question, a conceptual question, just to get an intuition of what these quantities are. If the acceleration is 0, does that mean that the velocity itself is 0? Okay. Maybe that gives you enough time to think about it. All right. So the answer is no, of course not. The acceleration is a change in the velocity, right? If the acceleration is 0, that means that the change in velocity is 0, which means that the velocity itself is constant, right? That means the velocity is not changing. But it can have a non-zero value, right? It can be constant at any value, right? So I could be in my car at rest, so the velocity would be 0, and I'm not accelerating. So in that case, they are both 0, right? But I could be on the highway going at 60 miles an hour, and I put the cruiser control, right? That's what it's called. Anyways, I put the thing that keeps the speed the same. And at that point, if I'm going in a straight line, I won't be accelerating, but I will be going at a non-zero speed and a non-zero velocity. Okay. So hopefully that makes sense. And so just as with the instantaneous velocity, right, we can define an instantaneous acceleration. And so what this is nothing more than the average acceleration, the definition of the average acceleration in the limit that the interval in time, the time interval, becomes infinitesimally short, meaning it becomes really, really tiny. It goes to 0. Okay? So this is what this means. A is equal to instantaneous acceleration. Notice that I didn't put that little bar, right? So if I don't have a bar, that means that it's not average. This is the instantaneous. Is equal to a change in the velocity divided by the change in time as I take the change in time to 0. And it has units of meters per second squared. And so again, I define it. You can just grab the definition. The acceleration is again going to be a slope in the graph of v over t. So here's v, velocity as a function of time. And so the average one is going to be the slope of that graph from 2 points, and I can take that limit in where I take the interval to be 0. Okay. All right. I think that's my introduction. So that's the basic idea is if you want to describe the simplest objects in physics, so describe just the position and movement of particles, you necessarily have to introduce calculus. Calculus comes in at the level of trying to put some meaning in what these limits, these infinitesimal limits mean, right? How do we rigorously define the limit as where I take the separation between the value of the difference between the velocity at 2 different points divided by the difference in time. The point is that both the numerator is going to, both the numerator and the denominator are both going to 0, right? But they're going to 0 in such a way that this ratio is finite, and it's going to be equal to, in this case, deceleration. And so what we're going to do is give a little bit of meaning to this, and we're not going to introduce this as it is normally in calculus, but instead we're just going to try to solve this, take these limits numerically. Okay. So maybe let me stop for a second, see if there's any questions, and maybe what I'll do is I'll take a quick water break before we continue. But if the TAs have any questions, maybe it's a good time to ask them.
No new questions. Everyone seems to be following along quite well.
Okay.
Actually, so.
Sounds good. So how about I take a quick second to grab some water. And what we're going to talk about next is start introducing calculus, or some bits of calculus. Okay. So I'll leave this up for a second, and I'll be right back. Okay, and we're back. Should I go ahead, guys?
Yep, you're good to go.
Okay, sounds good. Okay, so calculus is, I mean, at least from a physicist's point of view, one of the most powerful fields in physics and math. And the history of it goes back quite a bit, all the way back. Some of the concepts go as far back as to ancient Greece. But the formulation of the field is largely attributed to Isaac Newton and Gottfried Leibniz, who made important and independent contributions at the time. The history is actually kind of interesting between the two individuals, and the claims of who discovered what when. It's kind of interesting, but from a simple point of view, it doesn't really matter. So we could just simplify things a little bit here, which is, I think this is a typo. Oh no, it's not a typo. So Leibniz's interest lied primarily in setting foundational notation and mathematical rules, while Newton's interest was always in trying to describe the motion of physical objects, which is really what physicists, well, I mean, Isaac Newton is a foundational individual that set in motion, I mean, no pun intended, but it set in motion all the modern day physics. So everything that we do in modern day physics can go far back, go back to Newton's foundations. And so calculus is roughly divided into two subfields: differential calculus, where the interest lies in trying to calculate the rate of change of quantities, or equivalently the slopes corresponding curves, right? And so this is what we're going to focus on ourselves, since this is what we were just interested in. We just introduced, right? The second half is interested in is the integral calculus, where the interest there is in the continuous sum of functions, or equivalently the areas on the curve of a function or between different functions. These are tied together, and so these are closely aligned. And so in a class in calculus, you would learn about both of them simultaneously. And the first part is the one that you would be first introduced, and that's what we're going to be covering here. Okay. And so differential calculus, as I said, is mostly focuses in trying to make sense in defining these limits. And so this d over dx acting on a function is the instantaneous rate of change of that function, also known as a derivative. Okay. And what that is, and here I'm defining it with this notation of a, which is really what I'm going to be using throughout. And this delta a f acting on f of x divided by 2a, I can just define it. I can just bring back the definition in the very first slide on these notes, and that's going to be equal to f of x plus a minus f of x minus a divided by 2a. Okay, and so here, let me bring my handy dandy iPad. Oh no. Okay. Oh, wait, does this work? Sorry, I just realized that I brought the wrong adapter. Let's see if this works. Nope. All right. Sorry, folks. No iPad today. Okay. Well, all I've done, what I wanted to show is that this definition is equivalent to the ones that we were working with in the previous slides. I just defined the separation between the initial point and the final point as 2a. Okay. So the difference in the 2 points is equal to 2a. And I just have aligned them so that they're centered. The distance between, hey, oh, what is that? There's a USB and all I need is just a USB adapter to a USB-C. And I thought this would work, but it's not really.
Let me go back here. You said I have the. Can I see that?
Yeah, let me see that one. Oh yeah, this one works. Great.
You good? Okay.
Yeah, awesome. Thanks. All right. Let's see if this works, folks. I know how much you guys love the iPad, right? So it's a crowd pleaser. Let's see. Aha. Oh, you're in luck. Not gonna live up to the expectation. Right. All right. Ooh. Okay. All I wanted to do is just relate this definition. This is simple algebra. So here, for example, I was using delta x over delta t, right? And so in general, we're interested in functions, and I'm going to be labeling the dependent variable x, but I can also, or the independent variable x, but I can also call it t. It doesn't really matter, okay? And so the derivative of this function is equal to the limit as delta x goes to 0 of the change of f divided by the change in x, okay? So you have some function, and this is x of f, x of I. This is my this is change in delta x, right? And this is the change in delta f, okay? And so all I did was that I let x of f to be equal to x plus a, and x of I equals to x minus a. And so in this case, what that means is that the center point between the two of them is going to be defined as x, okay? And then the distance is going to be, this distance is going to be 2a, right? You can just check that. X of delta x is equal to, by definition, is equal to this, which is equal to x plus a minus x minus a. You see the x's cancel while the a's add up. Sorry. Can you see it? No, you cannot. There we go. Can you see it now? So I'm left with 2a. Okay, and so because of this, I can just use this definitions. Taking delta x to 0 is equivalent to taking a to 0. And then on the top, I have xf minus xi divided by 2a because that's delta x, so I already proved that. And so here I'm just going to rewrite this one more time as f of x plus a minus f of x minus a. Okay. Oh. Okay. And so that's all we did in writing these expressions. So they're equivalent. You see, you have f of x plus a minus f of x minus a. Okay? And so this whole thing, this limit, I already said a few times, is known as the derivative of f as a function of x. Okay? And this is, of course, the instantaneous rate of change of the function, right? You're taking the change in the function divided by the time that, or the interval over which that function has changed, and you're taking the limit as the interval goes to 0. And so determining this analytically is not always easy, right? Showing what this derivative, what this limit is for different functions, it's not always easy, and that's part of what the calculus, what a class in calculus will cover. But it turns out that doing this numerically is actually much easier. And so this is why you need a calculus course to be able to solve these things, or evaluate some of the things that we're going to show you numerically. And to convince you of this, the first exercise that you have to do is the following. Write code to take the derivative of any function f at x for a non-zero value of a, okay? And so what this means is that what we're going to do is evaluate this difference, this ratio, for any value of a, okay? And then we're going to worry about the limit, okay? So we're going to worry about the limit second, okay? But first, let's just write code to take this difference, the difference of the value of the function at x plus a minus the value of the function at x minus a, and then divide it by 2a, okay? And you can do this quite easily. You can define a function which is a function of a function. And this is quite nice. You can do this quite nicely in Python, okay? And so here I'm defining a function that I'm calling fin underscore deriv. So meaning finite derivative. And this is going to be a function of f, where f is the function that we want to evaluate its derivative. It's a function of the location of where I want to evaluate the derivative. It's a function of a, okay? And so, and then I describe here in words what this is. So it's just evaluating the rate of change of f as a function of x, where the final point is equal to x of xf, which is equal to x plus a. The initial point is x minus a, okay? And the difference between these two is just equal to xf minus xi, which is equal to 2a. Right? And so here, this is just comments. You see the comments are much longer than the code. This is my code for taking a derivative. I just grab the numerator, which is f x plus a. Notice the syntax, right? I'm defining this function. The input is a function, right? And I don't, in the input, treat it any differently than any other input, okay? It's not until I grab the function and I put parentheses next to it that it's obvious that it's a function, okay? This has to work only for a function. And so the numerator, well, that's what this num means, is equal to the difference of f evaluated at x plus a minus the difference of f evaluated at x minus a, okay? And then the denominator is equal to 2 times a, nothing more, okay? And so what it returns is just this top part divided by this bottom part. Easy, that's it. That's all I had to do. And this works for any function of f. Any function f, okay? That's the claim. I don't have to know anything about the function for this to work. Okay, so there has to be a catch, and we'll get to that catch in a second. And this catch is going to be in the context of convergence of the code. The point is that here I've had to introduce this a, but obviously this is not, when I take the limit as a equals to 0, the left-hand side does not depend on a, right? And so how do I make sense of that when I have to input explicitly a value of a, okay? And so to do this, we're going to use some simple examples, and we're going to test this code, and basically you have to be writing this code, right? Write your own code, but if you want to use this as a reference, by all means, go ahead and do it. And we're going to test this with the derivative of known functions, okay? And so here's a list of derivatives that are well known that you would learn in introduction to any calculus course, and that are very, very common in physics, okay? And so let's walk through them. The derivative, so here I'm setting c to be a constant, okay? And the first one is quite easy, and it should be quite obvious, which is the derivative of a constant is 0. Okay, what does that mean? Well, and why is that so easy? Let's look back. You can always think about that if you're let me plot my constant as a function of x. Oh, so if it's a constant, it just looks like a straight line, right? And this is c. And so it doesn't change with x, right? And so what is the derivative? The derivative with respect to x of c, well, is equal to the limit as delta x goes to 0 of c evaluated at 2 different points. Okay, so let me just evaluate it at this point, and then at this point. Well, the initial value is c, and the final value is c as well, right? And so I have the change delta c divided by the change in x, right? But this, for any value of delta x, the numerator is 0. And so this is just equal to 0 before you take the limit. So, in other words, the slope of this line is always equal to 0. All right, so the first one makes hopefully quite a bit of sense. The other ones are less trivial. And you don't have to know them by heart. I encourage you to memorize them. If you're going to be in any field of science, you're going to learn, in your calculus course, you're going to learn to derive this, and eventually it just becomes really useful to just memorize them because you use them so much. And so I think most of these are self-explanatory. So here we're taking the derivative of sine, where the argument is c times x, and you see that that's equal to cosine of the same argument, c times x, multiplied times c. Okay, so it changes the prefactor. Same thing for cosine. And in fact, in most of these cases, we're going to do this, we're going to test this for these functions. We're going to set all these coefficients equal to 1, except on this case. So this case is the only one that maybe we can look a little more closely. It's about that the derivative, since the derivative doesn't act on the constant, the derivative on the constant is equal to 0, there's a chain rule that you have to learn, but regardless, you don't have to memorize, you don't have to know about this right now. All you have to know is that the rate of change of this, of something like this, where you have a constant times x to the n, just lowers the power in x by 1, and then it multiplies the constant by a prefactor of n. Okay, so you see the n was in the power, it comes down, and multiplies c, and then x now is reduced by 1 power. The powers in x is reduced by 1. Okay, so you don't have to know these. As I said, I encourage you to memorize them. You don't have to understand where they come from right now. That would be a little preposterous for you to learn, for me to be able to explain to you where this comes from in a couple of lectures. That being said, what we can do is test these ideas numerically. Okay, we can actually test them, and so we can see if these are true or not. Okay, and so to do this, we have to test the convergence of our code. And this was the issue that I already alluded to. The derivative is only defined in the limit that a goes to 0. But and so what we have to do is test the convergence in this limit as we take a to 0. And so what we want to do is in particular plot the result. I think I meant to say resulting function. Resulting function as some value of x as a function of a. And in practice, the issue is that we cannot take a to 0. We can't take this numerically. This is not well defined. The reason is that if you're dividing by 0, You get an infinity. And so then the code doesn't really know how to make sense of this. And so what we can do is determine the derivative for a range of values of a, and test that as a has become sufficiently small, the answer no longer changes. And so it becomes constant with a. Okay, and so what do we want to do? We want to define so we're defining a derivative, right? An effective derivative, let's call it, of f of x, which is equal to the change of okay. And so what we're going to see is that for a given value of a, we need to test that this derivative remember, we're interested in the limit that a goes to 0. So let me put a equals to 0 there. We can't ever reach this point, right? But what we want to see is that if you determine some value of a, it starts to do something like this. And so you see that what I tried to do is that as you plot it for smaller and smaller values, it becomes flat. And that is equal to the value that it would have obtained it at a equals 0. Okay? Well, if you make a sufficiently big, then it starts to deviate. Okay? And so we want to see this kinds of plots, right? We want to see that it approaches a desired value, which we're going to make a flat line. Okay? And fortunately, we can test this because I already show you some tables of derivatives that already exist. And so you can test what the predictive value is and what your code gives. Okay, so this is meant to give you a little bit of confidence that you're getting the right results. Okay, and so as I said, what we're going to do is visualize the convergence towards the desired answer, but we can also we're going to want to introduce something that tells us about the error of the result. Okay, so something that allows us to visualize that the error that we're making is going, basically that the change of the function is indeed going to 0. Okay, and so, or that we wanted to see it be flat, right? So what we're going to do is calculate essentially the slope with respect to a. That's what we want to see. And so if the derivative is independent, so the derivative that we're calculating is independent of a, then the derivative of this function, of the derivative of f, and the derivative of f, the derivative of the derivative of f with respect to a must be 0. Okay, this will be clear in a second. So what we want to do is calculate first the derivative at a plus delta a. Okay, so some small value of a. And so calculate some small value of a plus a shift. Okay, then we're going to calculate this at an even smaller value of a, smaller by this amount delta a. So this is the derivative at this point. This is the derivative at the other point. And what we're going to do is take the difference between the two values and divide them by the shift in delta. And in order to us to visualize this better, we're going to multiply it by a factor of 10, or 100. Sorry. This is just so that we can see it a little bit better. It doesn't really make a change. You can just scale this not by 100, but just 1. And we're going to call this thing sigma a. Okay. So this is going to tell us a little bit about the error that we're having. That's why I decided to call it sigma a. Okay. And so what is this doing? If I grab 2 points of the derivative of the function, this is just calculating, say, this point, and it's dividing. So it's grabbing the difference and then dividing it by the shift on the two, which is delta. Okay, so it's shift in a. The change in a, I'm defining it to be delta. And so sigma a is just going to be the ratio the difference, let's call this value F1, let's call it G1 or H1, let's say. There we go, H1, H2. So I'm just the difference between the two divided by delta, taking the absolute value because I don't really care about the sign, okay? And then I'm gonna scale it by 100 so I can see it. That's what I'm calling sigma A, okay? So that's that. And so the limit that this goes to 0, that's telling me that the difference between these two is going to 0, okay? Did I do this right? Oh, no, sorry. I gave a different definition. So I'm taking the derivative at that point. Okay, this would work as well. I'll get back to this. I forgot what I did in this slide. So we'll come back to this and clarify this issue. But before we clarify this, I think we can just jump into the bulk, so the main point, which is to test the convergence of these functions. So we can just visualize as these approach to the desired value, okay? And so this part is independent of sigma, and we're gonna come back to sigma, and I gotta go back to look at my code to see what exactly I plotted. And so what we're gonna do is vary A from a very small value of 10 to the negative 5 all the way to 0.1. I do this in semi-continuous points, okay? In my code, I did this in steps of 10 to the negative 3, so it's tiny little points, okay? So, and I fixed x to be at 1. This is just arbitrary. I could have picked any other point, but I said x of 1 is perfectly fine, okay? So you can use different steps if you want, perfectly reasonable, nothing really holding you back to using a different value. That's just what I chose. And so what we're gonna do is test our code by taking the numerical derivative using the previously defined function for the following functions: the exponent, so an exponential with respect to x, a logarithm with respect to x, sine of x, cosine of x, and then a polynomial. Okay. Why did I choose this polynomial is largely arbitrary. There's really no good reason, except the derivative of this will be equal to 1. Has to be equal to 1. Oh no, this is let me go forward. I think I ended up taking a different, oh no. Yeah, there's a typo. Let me fix it. So this is supposed to be, I define this so that the derivative is 1, which means that this has to be this polynomial. So let me correct that right away. There we go. Okay, and we're back. Okay, so the first thing, test your code for the derivative of each one of these functions as a function of a for a fixed value of x, okay? So let's walk you through this. And I'm gonna have to go back. I'm gonna have to look at my code to see if this is really what I'm determining or whether it's what I just said that I was doing. Either way, these two should converge in the limit that. I have to think back. I have to look back at my code to see what I've determined for sigma A. But the most important part is the top one, okay? So what I'm plotting is the finite difference in the exponent of x, the exponential of x, divided by 2a as a function of a. So you see a is over here. And if we go back to the slides, the slides with the derivatives, you see here's the derivative of the exponential. And what you see is that the derivative of the exponential, let's simplify these expressions a little bit. So let's define first the derivative of an exponential of x? Well, I can look at this table and I see that the derivative of exponential where x is being multiplied by c is equal to c times exponential. But in this case, c, you see, is 1. And so this is just equal to an exponential of x. That's the beauty of exponentials, okay? So that's the first identity. And so we need to check this. The second one is that the derivative of sine of x. If we look at the table, we have the derivative of the sine of c of x is equal to c times cosine of c of x. Well, c is equal to 1, so this is just equal to cosine of x. And I can keep doing this for the other ones. The derivative of the cosine of x, okay? Well, the derivative of the cosine of c of x is equal to negative c sine of c of x. C is equal to 1, so this is just equal to negative sine of x. What other ones do we calculate? We're going to calculate the derivative with respect to the logarithm. Okay? So this is equal to, if I look at my table, I see the derivative of the log of c of x is equal to 1 over x. Huh, interesting. You see, the answer does not depend on c. Okay? And this you can also understand from knowing some properties about logarithms, but we don't have to go there. And then the last one is this funny derivative that I defined that was x cubed divided by c divided by, plus x to the 8th. X to the 4th divided by 8, okay? And so something that you should know is that the derivative of the sum of functions is equal to the sum of the derivatives of the individual functions. So that's that, okay? And then I see this expression right here. Notice, in my case, c is not equal to 1 for this example, right? I have c is equal to 1/6 for this case, and then 1/8 for this case. And so the point is that the derivative of these terms, the factors of c is just move forward. And so you see I just lower the power of each one by 1. So the first term is x cubed. Well, that becomes, I get a factor of 3 in front, right? Because in here I see the n is the power of x, and it gets lowered. So that brings down a factor of 3, and then 3 becomes 2. Very good. And then the other term, I follow the same prescription, right? So I have 1/8 that just comes for a ride. The 4 comes down, and then I'm left with x 4 minus 1, which is also known as 3. And then you see that the 3 cancels a 6, giving me a factor of 2. And then the 8 cancels a 4, leaving me with a factor of 2. And so, sorry, see that you can't see that. Good. So now you see that in the limit, as x goes to 1, I have 1/2 divided by, I have 1/2 plus 1/2, also known as 1. Which is why I decided to create these factors of 6 and 8. Okay, so this tells us exactly what we should expect. And so what we can do is just test that calculus is right numerically, or that these calculus results are right. All right, so now let's go forward. Okay, so here I have my code plotting the difference, the finite difference divided by 2a as a function of a. You see that as I take a to be, I go from 0.1 all the way to 0. And I think I exaggerated the values here that I wanted you to plot. Oh, no. Okay. No, that's right. Okay. So from 0.1 all the way to 0, you see that it starts to approach some number here. And that number is nothing more than the exponential exponential to evaluate at x equals 1. So it's just e. Okay, that's what that number is. And that's what I plotted in this line. So you see that it is indeed convergent to that value. And this systematic error that I defined, that now I'm getting confused myself, so I'll double check. It is indeed going to 0. I did the same thing for the log, right? So that's this function right here. And I should be getting 1 over x, right? But remember, I fixed x to 1, right? So 1 over 1 is equal to 1. And you see that indeed the derivative on the log is going to 1 as I make a sufficiently small. Good. Okay. So here's the cosine. Same thing. Sorry. Here's sine. So the derivative of sine, you see, is approaching this number, which is equal to cosine of 1, which is what we expected, right? The derivative of sine is equal to cosine. Good. And then there's cosine. The derivative of cosine should go to negative sine. And you're seeing that indeed it's approaching this number and it's plateauing, so it's becoming flat. So the difference, the derivative on it is going to 0. And that is equal to, that value that is approaching is equal to negative sine of 1. And then last but not least is this function that I just talked about, this polynomial that is x cubed divided by 6 plus x to the 4th divided by 8. Taking the derivative of it, again, converges for small values of a to the value that I expected, which is x squared divided by 2 plus x cubed divided by 2, all evaluated at x equals 1, which is 1/2 plus 1/2, which is equal to 1, and that's this number. Okay. And okay, so I think that's a good place to stop for a second, and I'll let people to trickle in questions if they have any. And meanwhile, I'm going to check to see how I define the sigma and make sure that I didn't do something silly. So I'll let you guys answer whatever questions may be coming in or comments.
Nothing yet. I think you're doing a good job of explaining it if there's not many questions.
It's very kind of you to say. Let me see. No, I did. This is silly. I don't know why I did this. Oh, no. Okay, I did it right. Oh. I confused myself. So, no, I am calculating exactly what I'm quoting here, and that's exactly what we should be doing, and that's exactly the same thing that I suggested in my... Yes, good. So that's exactly the same as what I was saying over here. So the point is that these points, h of 1 is going to be equal to delta a f divided by 2a. And h of 2 is equal to the derivative with respect to a larger value of a, which is a plus delta divided by 2 a plus delta. And so the sigma that I wrote down is equal to 100 divided by delta. Oop. Which is exactly what appears in that slide. Okay, so I think we're good. Sorry. I think I just confused myself. Okay, so now let's look back at these graphs. The goal is to get you to reproduce these graphs, and it's to both give you confidence that you're doing things correctly, and second, also, so that this is actually quite a useful tool, right? If you haven't taken calculus, now you know how to take the derivative, and you can do this numerically. And so if you ever have some calculus homework and you're second guessing yourself on the results that you're getting, then you can just check your code. You can just run this, evaluate this for any function, and double check that you're getting the same answer, okay? So let's look at the sigmas. So what is sigma? Sigma is telling us the difference. How is my answer, which is this thing, changing with respect to A, right? And you're seeing that and I scale this by a factor of 1,000. So really the change is quite small in the scale. And you can see this by the fact that this numbers, although it looks like it's very sensitive to the value of A, you can see that this is only changing on the fourth significant figure, right? So it's only changing on the fourth significant figure. So it's actually the difference between these values. It's not that big, right? It's a sub% level, okay? And so here I've scaled this by a factor of 100 for us to dramatize the value, right? But you see that indeed, as I take A to 0, this is approaching 0, which is what we expected, okay? And same thing for all these plots, right? You see again the variation is on the fourth significant figure. So this curvature is really dramatizing the convergence. Any of these values would have been pretty good at the sub% level. Same thing over here, right? You see the variations on the, in this case, it's actually on the, no, it's on the fourth significant figure. Same thing here. That is maybe converging a little bit slower. But the sigma is indeed going to 0, and you know, you can actually take sigma A to be fairly small, and we're going to take it to be 10 to the -3 in the subsequent exercises, because that's pretty good. Same thing here for this function. You see the convergence is pretty good, and you know it is approaching 0 as we expect the value of sigma, which is telling us how sensitive our result is with respect to A. And so here I would claim that in this region we have indeed converged, and it depends ultimately in what level of precision or accuracy you're hoping your results to be, right? If you're shooting for some level of precision, then you can zoom this in even further and check that indeed you are converging to some level of precision. So in this region, we already converged to sub% level. If you're interested in a fraction of a percent, or X amount of a percent of your result, then you might have to do a little harder work. But I think for most purposes, this is pretty good. Okay, so the next thing is, now that you've determined that indeed your results are converging as a function of A, this intrinsic separation that we've calculated, then pick a small value of A, okay? One where you see that things are converging pretty good. And I'm picking 10 to the -3. You can play around with this even further. And the next thing is to now start plotting the function that you're after and its derivative, okay? So in this case, I'm just basically repeating, just showing that the results reproduce the expected functions, not just at that one particular value of x that I chose, which was x equals 1, but it actually converges for any choice in x, okay? And so here you can see that if I make, so what I'm plotting is the function that I'm taking is derivative as a function of x, and then on the bottom I'm taking the derivative. The blue is the numerical derivative, okay? And then the green is the expected value according to the little table, the handy table that I gave you. So let's go back. Here it is. And so this is what I meant, that after some time you start memorizing these things. So you see the derivative of the exponent is an exponent, right? So here my input function is an exponent. And so we want to plot the derivative as a function of x, and I've done it here. The blue line is what I get, and then the green line is what I expected to get. The green points, sorry. The green points is the right-hand side, okay? And you've seen that indeed, at least by eye, these look very close to each other. Then on red, here is the function that I want to take the derivative. So in this case, I'm plotting sine. And then the blue line is the derivative of sine. And then the green points are what I expected to get, which is cosine of x. Okay? You can see, again, remarkable convergence or agreement. Second, and then the last one that I did is I did the same thing. So I took the derivative of cosine, which I expected to be negative sine. Here is cosine. Here's the derivative of cosine. The blue line is what I get. And then the green points is the expected value. And you see, again, they agree remarkably well. Okay, so I think that is the first set of exercises just to get you warmed up, get you used to derivatives. Maybe what you can do is send us a comment to see if this makes sense to you, if there's any questions that are lingering. I would be particularly very interested to hear from those of you that have not taken a calculus course, if this introduction to rates of change and what we mean by taking the rate of change of a function, either, well, numerically in particular, if that makes sense to you. If there's anything that is not really clear, I would like to hear in particular from you, but anybody else, if you've taken calculus and you have any comments or feedback, I would like to hear from you. So maybe I'll give you a minute, and then I can tell you while you send your comments, questions, or suggestions. Let me tell you what we're going to cover up next. And this is, I think, what we'll do is that we'll start this up next time, which is we're going to start thinking about differential equations. And the reason why we care about this is, so first, we need to understand what differential equations, but the reason why we care about this is because differential equations appear in physics all over. I mean, they appear in all the sciences all over. And so many of the most important equations in physics are either differential equations or can be casted as differential equations. So even F equals ma, so Newton's force law is the differential equation in position, right? So A is equal to the second derivative of position with respect to time, wave equations, the Schrodinger equations, Maxwell's equations, all of these, and many more can be written as differential equations. So what are differential equations? They're equations that relate one or more functions and their corresponding derivatives. Okay, and so one simple example of this is, say you have a function f of x, and you evaluate its derivative, and you associate that with another function g of x. Okay, and this is exactly the differential equation that we're going to be considering, the simplest of all, and we're going to show you how to solve this numerically. Okay, for any function of x and the right hand side g. So the question is, what we're interested in in particular is, what is f given some value of g? That's really what we're going to try to answer in the next class. Okay. All right, folks. Any last minute questions, comments that we should address?
Yeah, there was a really nice question from J.U. Chu from Xi'ai, Taiwan. They ask, this is not relevant to the material, but I want to ask, how is Taylor series applicable in physics? I just started learning it and was wondering how useful it is in other fields.
All right. Anybody want to take this on?
Just as a quick answer to the question, I would say that yeah, we use Taylor approximation quite frequently. It's kind of the first step approximation that we make. We expand functions that are too computationally heavy or complex, and we Taylor expand them to the first few terms depending on what our particular needs are. So it's actually quite useful for approximation purposes.
Yeah, perfect answer. Yeah, I absolutely agree. So Taylor expansions are remarkably powerful in physics, and I would say most sciences. It's kind of the grounding idea behind how most physics problems are solved. You try to solve the simplest systems, and then you try to introduce complexities that alter the structure of the system bit by bit, and you do this by assuming there's some parameter that is small, and this is basically the same idea of Taylor series. You're expanding some solution or some function about some point, and you're expanding about some parameter that is a distance away from that point to be small, and so so these ideas are adopted and quite universal in physics. Yeah, I did not want to do Taylor series, but since we are already introducing concepts of calculus concepts, we can maybe start playing around with doing problems related to Taylor series, Taylor expansions. Oh, no reason why not. Cool. Anything else?
Yeah, there's some positive feedback about your explanation today. It seems that people have found it quite helpful, and they might need to re-go over it because there are new concepts, but it seems a lot of people are striking value from it.
Awesome. Great. Yeah. I would be interested to hear thoughts on people that have never taken calculus, see if this is you find this accessible. The goal is not to make this overwhelming at all for anybody. We want to make you see the fun and joy in the sciences and computational sciences. And so we want to make sure this is fun and accessible to you. So if there's anything that is making that, if it's making you feel overwhelmed, we don't want to do that. So so if it's feeling not overwhelming or it is, either way, we would like to hear your thoughts about that. Cool. Anything else? Or
No, I think that's it for now.
okay, awesome. Okay, so as I said, so what we're gonna cover next is differential equations. That's what we're gonna do Thursday. We're gonna get you to solve some simple differential equations. Depending on how fast I talk, maybe we'll start jumping into models and models for infectious diseases. But I would prefer not to, so we might leave this for next week. But as I mentioned, next Thursday, we're going to have a nice introduction to quantum mechanics from Dr. Aslam. So I would encourage you to definitely tune into this, whether you've been following along with the Python course or not. I would encourage you to check it out. So let me look at what's next in REYES. So think I remember what it is. Oh, yeah. So next, I would encourage you to check out this session by my colleague, Christopher Fleming, who's going to be giving you an overview of the admissions process here at ODU in case you might be interested for undergrad or grad school. So he will be able to answer many of your questions. Even if you're not interested, I would check it out just so you hear about admission processes, even if you're not interested in ODU, but maybe interested in other universities. A lot of the admission process is going to be universal. So, you know, if you want to hear questions about the TOEFL or entry exams and all these things that are universal for many universities, I would encourage you to go in and talk to an expert who may be able to answer your questions about that. And just so you know, he's Assistant Vice President for Enrollment and the Executive Director of Admissions here at ODU. So certainly an expert on the topic. So stay tuned for that. Okay, so with that, everybody, and I'll see you on Thursday.